So to demonstrate how to find the slope of a tangent line on a polar curve, let's consider the following cardioid. R is equal to 2 plus 2 times the cosine of theta. So this would be considered a cardioid with the extreme point on the horizontal side. I can tell it's a cardioid due to the fact that the coefficient of 2 on the cosine is the same as this 2 right here, meaning that it'll come back and boop the origin right there, or excuse me, boop the pole right there, and then keep going. So what we're going to do is consider the angle pi over 6, and we're going to try to figure out the slope of a tangent line right at that point. I predict we'll get something that's kind of large and negative. So with that in mind, we are going to start with x is equal to r times the cosine of theta, and we're going to go ahead and plug in what r is equal to. R is equal to 2 plus 2 times the cosine of theta. We'll be multiplying that by the cosine of theta. What I'd like to do is distribute the cosine, and then we'll differentiate the function in this form. So that's 2 cosine theta plus 2 cosine squared theta. This is as opposed to the formula that I gave in the last video that had a whole bunch of r's and cosines of thetas and sines of thetas and dr d thetas in it. We'll just go ahead and differentiate it in this form. So dx d theta will be equal to derivative of 2 times the cosine of theta with respect to theta will be negative 2 sine theta. And then we'll need the power rule as well as the chain rule for this one. So this will be 2 times cosine theta times the derivative of the cosine of theta. And we can simplify this expression to be negative 2 sine theta minus 4 times the sine of theta times the cosine of theta. That takes care of x. Now let's take care of y. Y is equal to r times the sine of theta. If we substitute in what r is equal to, that'll give us 2 plus 2 times the cosine of theta times the sine of theta. Once again, I'm going to distribute that through. So 2 times the sine of theta plus 2 times the sine of theta times the cosine of theta, just reordering it. Then dy d theta is going to require simple derivative for the first one and then product rule for the second one. This will be 2 times the cosine of theta plus 2 times, and then we'll apply the product rule. This will be first times derivative of the second plus second cosine of theta times the derivative of the first. Derivative of sine of theta is cosine of theta. And if we simplify this expression a bit, we are going to get 2 times the cosine of theta plus 2 cosine squared theta, just writing this term first, and then minus 2 sine squared theta for the second part. Now at this point, if I want to keep them separate, that's fine. But if I want to combine them into one big expression, dy dx is going to be equal to the derivative of y with respect to theta goes on top, 2 times the cosine of theta plus 2 times the cosine squared of theta minus 2 times the sine squared of theta, all over the derivative of x with respect to theta, which is this guy right back here. Negative 2 sine theta minus 4 sine theta cosine theta. So this is the expression in terms of theta of what our derivative is. At this point, I'm going to call back to the original problem that says figure out the slope of the tangent line at pi over 6. So when I'm plugging in pi over 6, 2 really good things to know are going to be what is the cosine of pi over 6 and what is the sine of pi over 6. Cosine of pi over 6 is root 3 over 2, and the sine of pi over 6 is going to be 1/2. That way I can start making these substitutions directly into the expression for the derivative. So dy dx evaluated at theta equals pi over 6 will be 2 times the cosine of theta, that's root 3 over 2, plus 2 times the cosine squared of theta, so root 3 over 2, quantity squared, minus 2 times the sine squared theta, so that'll be 1/2 squared. This is all over negative 2 times the sine of theta, that'll be 1/2, minus 4 times the sine of theta, which is 1/2, times the cosine of theta, which is root 3 over 2. Obviously, there is a lot of simplifying that needs to take place here. Let's go through and try to do it term by term. 2 times root 3 over 2 will be root 3. If I square this number, I'll get 3 over 4. Multiplying by 2 will give me 3 over 2. So this will be plus 3 over 2. Square the 1/2, we'll get 1/4. Multiply by 2, we'll get 1/2. So this will be minus 1/2 all over. Negative 2 times 1/2 will be negative 1. This 4 will cancel out these two 2's very nicely, and we'll have negative 1 times root 3, so minus root 3. Continuing to simplify the numerator, we'll do that at the next line down here. 3/2 minus 1/2 will be equal to positive 1. And in the denominator, if I factor out a negative sign, I will have 1 plus the square root of 3. You'll notice that the two factors in the numerator and denominator are the same, just with an extra negative sign. So the slope of that tangent line is going to be equal to negative 1. Now, another problem of interest for this problem, and I will call back to this sheet when it is the appropriate time to do so. I'll keep that sheet right here so it's handy. Another good problem to consider is at what angles or at what values of theta will the tangent line be horizontal or vertical? So that's not how you spell question mark. There we go. At what values of theta will the tangent line be either horizontal or vertical? Now, call back to the last video. If either dx d theta or dy d theta are equal to 0 without the other one being 0, we will have either a vertical or horizontal tangent line. So what we're going to do is set dx d theta equal to 0. Call back to the last sheet. What was dx d theta equal to? That was this guy right here. So negative 2 sine theta minus 4 sine theta cosine theta. Negative 2 sine theta minus 4 sine theta cosine theta equal to 0. Now, to solve this equation, I intend to pull out a common factor on the left side, and that common factor I'd like to pull out is going to be negative 2 times the sine of theta. The rest is going to give me 1 plus 2 times the cosine of theta. Because it's factored and equal to 0, I can set the individual factors equal to 0. So either negative 2 times the sine of theta is equal to 0, or if we set this equal to 0, 1 plus 2 times the cosine of theta is equal to 0, which is equivalent to saying that the cosine of theta would be equal to negative 1/2. This one is saying that the sine of theta is equal to 0. This happens at two different angles on the interval from 0 to 2 pi, including 0 but not including 2 pi. This would be at 0 and at pi. For the other one, cosine of theta winds up being equal to negative 1/2 if theta is equal to either 2 pi over 3 or 4 pi over 3. Now, this doesn't necessarily mean that this is where you are going to see vertical tangent lines. Let's see, wait, is that right? Vertical? Yeah, vertical tangent lines. Due to the fact that we don't know whether or not dy d theta is also going to be equal to 0. So let's go ahead and solve that and then draw our conclusions. So set dy d theta equal to 0 as well. Dy d theta, calling back to the other page, dy d theta was equal to this expression right here, 2 times the cosine of theta plus 2 cosine squared theta minus 2 sine squared theta. I'm going to set that whole expression equal to 0. So 2 cosine theta plus 2 cosine squared theta minus 2 sine squared theta is equal to 0. First thing I'd like to do is we have two different trig functions present in this equation. I want to fix it to become one trig function. In order to do so, I'm going to use a Pythagorean identity, and change the sine squared of theta into 1 minus the cosine squared of theta. We get 2 cosine theta plus 2 cosine squared theta minus 2 times 1 minus cosine squared theta. If I were to distribute the negative 2 to these two terms and then combine all of the like terms, I'm going to rewrite it in a slightly different fashion. This will give us 2 cosine squared theta, and then this will be plus 2 cosine squared theta for a total of 4 cosine squared theta. And we'll also have the positive 2 cosine theta that we began with. And distributing this minus 2, we would get a minus 2 for a constant term. This equation is in quadratic form, therefore we should be able to factor it without too much difficulty. I'm going to start by factoring out a common factor of 2, since that doesn't seem to be bothering anything. Now with that in mind, this does factor pretty nicely, recognizing that the only way to get 2 cosine squared theta would be with a 2 cosine theta and a cosine theta. The only way that we're going to get a 1 for the last term is with a 1 and a 1. And then to make sure that we get a plus in the middle, it'll be a plus here and a minus here. This lets me know that if either 2 times the cosine of theta minus 1 is equal to 0, or cosine of theta plus 1 is equal to 0, that the value of the derivative of y with respect to theta will be 0. This equation gives me that the cosine of theta is equal to positive 1/2, and this one gives me that the cosine of theta is equal to negative 1. There are 2 places where this occurs. That's going to be at theta equals pi over 3, and theta equals 5 pi over 3. So 1 in quadrant 1, 1 in quadrant 4. This one gives me that theta is equal to pi. Now, doing a quick comparison with the values that we got for dx d theta being equal to 0, I see that there is one point in common on both of these, and that would be the value of pi. Now, what's going on at pi, I'm going to reference back to the other sheet. At theta equals pi, this is where the r value becomes 0. So at theta equals pi, r becomes 0. What it's actually referring to is this point right here. If both dx d theta and dy d theta become 0, that indicates that there should be either a corner or a cusp on our graph, and that is exactly what we see at the pole for this cardioid. Now, let's interpret all of the other values that we got. Oh my gosh, physics, stop being a dick. So, to interpret all of these values, we are going to see a vertical tangent at all of the theta values where dx d theta was equal to 0 except for pi. So this will be at theta equals 0, at 2 pi over 3, and at 4 pi over 3. We are going to see a horizontal tangent at all of the values at the bottom of the page except for theta equals pi. So that will occur at theta equals pi over 3 and 5 pi over 3. What I'm going to do is redraw the cardioid from the previous page and see if we can interpret this in terms of what we see on the graph. So at theta equals 0, that would be in this direction. We do, in fact, see that there is a vertical tangent right here. At 2 pi over 3, that would be in this direction right here. And yes, indeed, there is a vertical tangent right here at this point. And at 4 pi over 3, my guess is that we're talking about this other guy right here. So indeed, vertical tangents at 3 different values. Horizontal tangent is supposed to occur at pi over 3, which would be in this general direction. And yes, indeed, we see that there is a horizontal tangent line right here. And then on the other side of the x-axis at the same angle. So that's how we are able to determine all of our horizontal and vertical tangent lines for this cardioid.